I first learned about this conference shortly before I met Dr. Skowron in another conference in Dubrovnik. And I was very excited to hear about the topic of the conference because I had just begun starting to develop a research program which focused specifically on topological methods, not in ontology, but in philosophy of science. So I was absolutely delighted to receive the invitation to come to Warsaw. Now, one of the things that is unfortunate about trying to give a programmatic talk about a research program in 35 minutes is the necessary brevity of it. So as an advisory, consider this as the tapas edition, right? So I'm going to be offering you a number of small plates, each of which are appetizing, perhaps on their own, but none of them completely satisfying. So hopefully this will whet your appetite in two senses. It'll whet your appetite to try to learn more about the details of each of these, and also whet your appetite for the intellectual conversation that we are bound to have over lunchtime. So what I'm going to talk about is I'm going to talk about a general idea of trying to encode a notion of similarity that gets used quite often in different aspects of science and in philosophy of science using topological structure. Then I'm going to try to give some examples for how this notion of similarity, suitably encoded in topological structure, can be used to make surprising and detailed progress on a great number of philosophical questions. Intertheoretic reduction, emergence in science, the connection between scientific modeling and epistemology, counterfactuals in science, and then I'll conclude with a couple of broad ideas and some future directions. Now, the work that I'm doing here deserves many sorts of acknowledgments. So, for instance, a lot of the work on understanding similarity in terms of topology, I have been influenced by the scientific structural school. Actually, Professor Moorman's work has been influential for me. The work on intertheoretic reduction, the structuralists as well, and especially that of Jürgen Ehlers. The notion of emergence, the work of Jeremy Butterfield, and the contextual emergence of Bishop, Atmanspacher, and Primus. The idea of modeling in epistemology, actually, from Duhem, and from certain ideas of Hawking and Garroch in the late 1960s and early 1970s. And with regards to counterfactuals, I do have debts to Lewis, Van Fraassen, and Fred Muller. I wanted to acknowledge these influences because I'm not going to be here, because I'm not going to be discussing them explicitly when I talk about the details of the approach. I do want to emphasize that even though that I owe debts of acknowledgement to them, I think that my approach is distinct from each of these influences in important ways. And I'm open to discussing that during the Q&A period. Okay, let's get started. So what does it mean to encode a notion of similarity amongst a group of objects suitably mathematized by topology? Here's the way that I like to think about it. So we all know what a neighborhood system is for a topology. What you can think of the neighborhood system as doing is it's encoding a collection of qualitative similarity relations. And these similarity relations, the only relationship between them is partial ordering by inclusion, just given by the set theoretic inclusion. So this partial order only tells us that some similarity relations say that some sets are more similar to the point of which they are a neighborhood than others. But for those that are not related by inclusion, one can't say very much. Now, this is a very weak notion of similarity. It's qualitative. There's some structure, right, given by the partial order, but not very much. But this is what we need in order to, this weak notion of similarity is really all we need to do a surprising lot of things. For instance, one can give an interpretation for a limit of a sequence of mathematical objects using this kind of idea of similarity. a limit of objects On converges to O just in case the sequence eventually remains in every neighborhood of O. And that's naturally interpreted as the sequence becoming arbitrarily similar to O. That is, for any notion, qualitative notion of similarity you like to pick, the sequence eventually enters into that similarity class. Now, one thing I want to emphasize is that topology, the strict mathematical notion of topology, isn't the only way to formalize similarity. There's other related sorts of structures that one can use, some stronger, that is requiring more structure to the similarity relation, and some weaker, requiring less structure to the similarity relation. I'll be mentioning one of the former uniform structures later on in the talk. I don't want to suggest that topological structure is the way to understand similarity. I think it's one particular approach that is extremely insightful, but I think other types of situations may call for different sorts of similarity structures. So another thing that you can do, of course, is understand continuity in terms of similarity. So we have the usual notion of what it means for a function to be continuous. But if we understand the topologies on the domain and the codomain of the function as encoding a way in which the elements of the domain and the codomain, respectively, are similar to one another, then a function is continuous just in case every sufficiently similar variation in the domain yields sufficiently similar variation in the range. Okay, so when applying these sorts of ideas to scientific theories, we have to represent theories in some way. So here's a theory. Each of the points of the theory is going to represent a particular model of the theory. And I don't mean model in the sense of model theorists model, but more in the sense of an applied mathematician. So for instance, Ising models. These are lattices that have spin structure and some Hamiltonian. Another non-relativistic quantum mechanics. We have, in the simplest case, a Hilbert space, a wave function, and a Hamiltonian. Another, general relativity. These are going to be Lorentzian manifolds. You can think of these, to take an even simpler example, an example of this would be the full solution to the equation of motion of a classical particle, moving under the influence of gravity or colliding with another particle. These are all examples of a model of particular theories. So it's a full mathematical structure describing the state of affairs that the theory is meant to describe scientifically. So what we're going to do is we are going to think about a relevant way in which we want to say that those models are similar to one another. And we want to say that they're similar to one another just in case the situation that they describe, the state of affairs they describe, is similar. Now, there's going to be many topologies that we can pick. How do we know which one is relevant? So typically, my suggestion is that we should choose a topology that encodes similarity of relevant observables, relevant empirical predictions. Relevance here means makes a difference for the question or explanation at hand. So you have to pick a question or pick something that you want to explain, and you have to think about what kinds of empirical features are relevant for that sort of explanation. Then the topology should encode similarity of those sorts of empirical predictions. So in general, one of the consequences of this is that there's going to be no canonical topology on the models of a theory. And the reason for that is that different sorts of questions, different sorts of explanations will require to different sorts of things. Here's an example, going back to the Ising model. So one of the weird features of these sorts of models is that they undergo certain sorts of phase transitions. What you can think of this is it's a magnetic analogy to the transition, say, between boiling water and gas or liquid water and freezing, right? It's a different phase of matter, but it's the same sort of material. In these particular sorts of phase transitions, the magnetic susceptibility, which is the disposition of the material to be affected by a magnetic field, has this sharp peak And theory predicts that in fact, in the limit of a system having infinitely many constituents, that peak is infinitely sharp. So when we want to compare our predictions, though, the actual measurements that we make to the predictions of that theory with that spike, we have to think about what kinds of things are we actually measuring. As you can see from the plots and these little square dots, what we're actually measuring are particular points of temperature and magnetic susceptibility, for instance. We're not actually measuring whole regions over this space. So it's actually very difficult to measure directly that singularity. And so the relevant notion of comparison between the data and the predicted curve will have to be point-wise predictions, right? Points of that space. This is going to become relevant later on. Okay, so now that we have this idea of what it means for different models of a theory to be similar to one another, let's apply it to some particular topics. Okay, so intertheoretic reduction. So there's a sense in which we have often encountered a situation where we have a sequence of models of a theory. We want to say, in some sense, that a theory converges to another. Oftentimes people say, for instance, that Newtonian gravitation is the limit of general relativity under certain circumstances. I'll talk about that example later. So now imagine that you have the models of the theory that you are interested in taking the limit of, and you've put a topology on them. That is, you've encoded a relevant way in which those models are similar. And now you have a sequence of models that's doing something like that, right? It seems like it's converging towards something, right? But there's no element that it converges to. The idea here is this boundary here is not included in the set, but it seems that there's a sense in which you want to say it is converging to a boundary point. Well, one thing that you can try to do is you can try to describe a theory that you think is the limit theory. Take its models and throw it into this set. Include it as well as points in this topological space. That is, relate models of the new theory to the models of this theory also by their empirical predictions. Then the idea of reduction will be, in a certain sense, that the limit theory, the theory that this theory reduces to in the limit, is just going to be included in the boundary of this set. So the basic idea here is that a theory T prime is the reductive limit of a theory T with respect to some particular topology that's been chosen, just in case the models of T prime lie in the closure of the models of T. There's some variations on this that you can give. So instead of picking the closure, you can pick the sequential closure, which is not always the same as the closure. You can do all kinds of other things, but this is the basic idea. So let's look at an example. I just mentioned the case of Newtonian gravitation and general relativity. So one of the interesting features of general relativity theory in general is that it postulates a different sort of structure to space and time. In the Newtonian theory, one has space at a time that are kind of stacked on top of one another, right? Space, 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 right? Just in a linear sequence. In relativity theory, space and time are mixed up. At any particular point, there is a constraint given by the speed of light on the maximum speed that a massive particle can travel in. And that's given by this cone structure associated with that point. Now you notice here one spatial dimension has been suppressed. The vertical dimension is time. So what do these cone structures represent? They represent the constraint of the upper bound of the speed of light on massive particles. Think of it like this. If there is an upper bound on the speed at which a massive particle can travel, then there is a maximum distance that a particle can travel in a certain amount of time. So go up 1 unit, right, in these concentric circles here. In that amount of time, there's a maximum amount of space that one can travel in. And that's going to be given by the amount of space that is given in this direction along the cone. So in other words, light is going to be is the kind of thing that travels on the boundary of this cone at each particular point. And massive particles are the kinds of things whose instantaneous trajectory at a point has to lie within the cone. Now, there's a sense in which we want to explain then why the Newtonian theory, classical space-time theory, is so successful. It was successful and it continues to be successful in all sorts of applications, even though we know that it's totally the wrong picture of how space and time fit together. How can we explain that? Well, one kind of classical idea is the following. You imagine these cones opening up and opening up and opening up. And in the limit, as these cones completely flatten out, you get these flat planes, right? In the limit, these cones become planes. How can we make this idea precise? Well, what we can do is we can collect all the models of both theories together into one set and put a topology on them that encodes similarity of empirical predictions. These are things like measurements of field values at points or over regions. And one can do so as well in a way that fixes the speed of light as a constant in every model of relativity theory. One can do all of this and consider sequences of models of general relativity, models that have space-time structure like this that converge to models of this. And in fact, one can prove that such sequences exist. So there are sequences of models of general relativity that converge to models of Newtonian gravitation with respect to topologies that encode similarity of bounded observables. I put this in parentheses because I haven't defined exactly what this is, but these are observables that are defined with respect to fields, certain numbers of their derivatives on compact regions of space-time. Think of this as bounded regions of space-time. One of the interesting features, though, is that whether this reduction obtains or not, this limiting type reduction, depends on the choice of topology, right? Whether or not, in other words, a Newtonian space-time can be arbitrarily approximated by relativistic spacetimes depends on what we're approximating. And we can prove, in fact, that there are no sequences of general relativity that converge to a model of Newtonian gravitation with respect to topologies encoding global observables in a certain sense. I haven't defined what that is either, but in a rough and ready sense, these are arbitrary observables that are defined everywhere on the space-time. Okay, so let's move on to emergence. It's been said that emergence is a notorious philosophical term of art. I tend to agree with this. I, too, will then proceed to ignore my own warning and give yet another definition of emergence, but one which I think is technically precise, one which you can use to prove theorems about what kinds of properties are emergent. Now, often in these sorts of discussions, people make a distinction between ontological and epistemic emergence. What I'm going to say is that because all of the work happens inside the models of a scientific theory, whether you want to consider this as epistemic or ontic emergence will depend on your attitude towards scientific theories. If you're a very, very strong sort of realist, you might want to consider it ontic. If you're not, or even a moderate realist, you might want to consider it epistemic. Here's the kind of situation that I'm interested in. I'm interested in emergence of properties of systems in limits. So this sort of emergence that I'm interested in is a notion of emergence which is, in fact, closely connected to this limiting notion of reduction that I just spoke about. This is a notion of emergence which is very common in physics. So the kind of situation that I have in mind is we have some theory, and associated with each model, there's some property. So for property P, I'm going to have a valuation map, VP, which maps a particular model into a property space. This space is just going to encode the possible values of a property. If it's a categorical property, then the possible values are 0 or 1. So an example is blue, right? That's going to be a 0, 1 property. And this property space itself comes with topological structure, right? It's because these properties, or at least many of them, are observables, and those that aren't, there's often a topology that automatically comes with it. For example, real value quantities automatically inherit the topology of the real numbers. Okay, so suppose that a topology on models is given, as is a sequence of models, such that that sequence has a limit. Then I want to say that a property of the limit model is emergent with respect to this sequence and with respect to that topology, just in a certain sense in which the valuation map and the limit don't commute. So in other words, the valuation map of the limit model is not equal to the limit of the values. So what would be an example of this? Let me skip forward to give you this example. So in this example, for any finite system, this peak is always not infinitely sharp, right? But for larger and larger systems, it gets sharper and sharper and sharper and sharper, until in the infinite limit, at the limit point where the system has infinitely many subsystems in it, this function is discontinuous. So one of the features that is emergent here is a discontinuity in this curve. And this discontinuity plays a very important theoretical role in the theory of phase transitions. Under some ways of approaching the subject, it's essential to the definition of phase transitions, in fact. So in this sense, if one does understand this discontinuity as a part of the definition, what we would have in this sort of example is phase transitions being emergent. The property of a system of having this type of behavior is an emergent property because none of the finite systems leading up to the limit have it, but the limit system does. So part of my justification for saying that this ought to be called a notion of emergence is that, one, novelty. The emergent property is explicitly new, right? It's something which does not eventually, doesn't appear in the sequence. Now, there's some technical details here. You might have an initial sequence of initial subsequence, initial segment of the sequence where it appears and then it disappears. There's a lot of technical variations and modifications that one can make to this basic idea. I just wanted to get across perhaps the most basic version of it, which conveys the essential idea. Another is that it is the explanatory features of this. So the model in the limit theory is not derived from the limiting theory. So if we have a situation where I had before where the limit model is a model of a different theory, in the phase transition case, it's a model of infinite systems, whereas in the case inside the disk, these are finite systems. This model is not derived. So it's posited and a relationship between them is exhibited. So this is, in other words, encoding a sense in which the emergence here is surprising. If you just knew about the limiting models, right, you wouldn't be able to derive the feature of the limit model. Another feature, which I think is nice, is that we can understand emergence here as a relation between models and a similarity relation. There's no need for explicit invocation of different levels or confusions about what is a level, what defines a level. And in fact, I think in physics there's good reason to be skeptical of any sort of strong notion of levels. But that can be a discussion that we can have in another day. So I talked about this example. Another example from the same case in relativity theory has to do with the notion of simultaneity, One of the features of relativity theory that is so interesting and strange and lovely is that the notion of what it means for different events to be simultaneous to one another becomes relativized to an observer. Different observers in general will classify different classes of events as being happening at the same time. Now, if you have a very small relative velocity to another observer, so you and I, for example, we have very similar trajectories through space-time. So our relative velocity is very small. The class of events that we're going to characterize, therefore, as happening at the same time are almost exactly the same. We have to look really, really close if we're able to distinguish them. But for observers that are moving at a very large relative velocity, they're going to classify different sorts of events as happening at the same time. So the natural question arises, right? Somehow we want to use this to explain why it's possible to use public transportation, right? You look at a schedule, right? You see a time. You think that it makes sense to look at a time and know when the bus is at least supposed to come, right? How is that possible, right? It seems to invoke a notion of simultaneity, which we know is just totally incorrect. Well, we have this reductive relationship, this limiting relationship that I talked about before. But nevertheless, we want to say that the description of the world through a Newtonian view has certain features which in that limit are emergent. And one of those is going to be the notion of an absolute simultaneity relation. So one of the things that one can prove, according to the definition of emergence that I gave before, is that in these cases where you have sequences of relativistic spacetimes that converge to Newtonian spacetime, absolute simultaneity is emergent in the limit. Okay, how am I doing for time?
Pretty good. 50 minutes or so.
Okay, perfect. Okay, so now modeling and epistemology. This is a bit of a different turn, but one I think that's very important. My influence here comes from a passage from Duhem. And this is Duhem on idealization from his famous book, The Aim and Structure of Physical Theory. I'm going to read this out because I think it's worth it. A mathematical deduction is of no use to the physicist so long it is limited to asserting that a given rigorously true proposition has for its consequence the rigorous accuracy of some such other proposition. To be useful to the physicist, it must still be proved that the second proposition remains approximately exact when the first is only approximately true. Such are the rigorous conditions that we are bound to impose on mathematical deduction if we wish this absolutely precise language, that is the language of mathematical physics, to be able to translate without betraying the physicist's idiom. For the terms of this latter idiom are and always will be vague and inexact, like the perceptions which they are to express. Now, you don't have to share Duhem's phenomenalism, that is, his belief that ultimately physics is about encoding our perceptions, to understand the point that he's making. The point that he's making, rather, is that when we prove theorems or derive consequences from certain mathematical models, if those consequences depend on the exact validity of the assumptions, either of the theorem or of the model, we can be led astray, right? We can be led into error. These types of idealizations in the literature are sometimes called Galilean idealizations. They are deliberate distortions in how a model, in this case a mathematical model, represents its target. They're often said to be eliminable in principle but not in practice. That's to say, if you knew enough about the detailed situation that you wanted to be investigating, you could eliminate this distortion and replace it with something less distorted. But what I mean by it's not possible in practice is that it seems that every model that we ever introduce distorts its target. There's always some type of misrepresentation that a model does about the thing that it's representing. A simple example with which I think we're all familiar, a block sliding frictionlessly down a plane. Now, in Newtonian physics, we can analyze given the initial conditions of the block, the trajectory of the block, right? Its whole trajectory down the ramp. But only under certain assumptions, right? We have to assume that the force of gravity is completely uniform throughout, that the ramp and the block are completely rigid, that there's absolutely no friction, that there are indeed no other types of interactions between the block and the ramp. All of these are idealizations, right? All of these are Galilean idealizations because they're distortions of the situation that's actually being represented here. So the question arises, how can we be justified in making any inferences whatsoever from a model to its target? Right? If we know that the situation is being deliberately distorted, how can we trust any sort of inferences that we can make? So we can take from this idea of duhem, or this statement of duhem, an idea of a kind of condition you might want to put on what it would take, right, for justification to transfer from model to target. So suppose that we have a collection of models of a theory, and we've determined what notion of similarity is relevant here, and we've encoded that in a topology on the models. Then we can formulate the following principle of stability. It says that one has justification to infer a property about a target from a model only if there is a neighborhood of that model, all of whose members share that property. In other words, the principle states that the stability of a property, that is, the invariance of the property under arbitrarily small perturbations in the topological space, is a necessary condition for inferring that property from the model to the situation that it's representing. So this principle actually gets used in relativity theory. So here's a statement from Stephen Hawking. Stephen Hawking states, the only properties of a space-time model that are physically significant are those that are stable in some appropriate topology. Here, my reading of physical significant properties are just those that one has warrant to infer of the model's target. And Hawking is right to emphasize here appropriate topology. One has to think ahead of time about what the relevant notion of similarity here is. So I think that this principle has some interesting implications. So one thing that you can show is that in general, there will always be properties of models that one is never warranted to infer about their target. Right? Any property which does not obtain on an isolated point of the space is going to, any point that doesn't have, for instance, the singleton of itself as an open set may have this sort of feature. To give you an example, consider the case of the block from before. And we did a precise calculation of the time that it will pass a certain location. You can ask, are we warranted to infer that it will pass that location at exactly that time? The answer is no, we're not warranted to infer exactly that. We're only warranted to infer, according to this principle, at most that it will pass the block in some neighborhood of that time. Excuse me, pass that point on that block, on the ramp, in some neighborhood of that time. The idea here is that an arbitrarily small perturbation of the model, say by changing the mass, changing the frictional term, changing the uniformity of gravity, may well perturb one away from that specific numerical answer. Now, I think this is scientific common sense. But it has a number of implications besides the one that I mentioned. I think this would be interesting to investigate whether these sorts of principle gives us examples of failure of transmission of justification. It's a topic of interest to some epistemologists. and whether or not this is actually just another version of Sosa's safety condition for knowledge avant la lettre. We don't have time to investigate that now, but this last point does suggest another sort of idea. So Sosa's safety condition is a counterfactual condition on what it takes for us to have knowledge. And it turns out that these kinds of things can also be used to that these kinds of structures encoding similarity can also be used to understand counterfactuals in science. What I mean by that are situations where we say, if phi were the case, then psi would be the case. Now, there is a well-known account of how to evaluate these due to David Lewis. Instead of going through some of the details, I'll just say evocatively kind of what they are. To evaluate one of these conditionals, we have to associate with every possible situation. For Lewis, these are possible worlds. A set of spheres. What these systems of spheres are supposed to do is they are encode a notion of similarity of possible worlds. So wider spheres indicate less and less similar. Closer spheres to the point indicate more and more similar. And so to evaluate this kind of conditional, what we have to do is we have to go far enough out until we find a sphere where the antecedent is satisfied. Once we find these, we then have to check to see whether the material conditional, the corresponding material conditional, is satisfied. This would be a cartoon of an example where it would be. We go out to the sphere S, we find the models where phi is satisfied. Turns out these are also models where psi is satisfied. So on this particular model, that conditional would be true. These are important because they play a role in understanding scientific law, scientific reasoning, dispositions, and many other topics in science, causation as well. But the one problem with Lewis's proposal has been, it seems to suggest that we have to have his usual way of understanding how these are supposed to work involve worlds with miracles, violations of scientific law. And people have been skeptical of the perhaps merely logical or metaphysically possible worlds that these are supposed to posit. And in particular, the similarity relation has been vague. But we can use this type of structure to try to understand how to understand similarity between models of a scientific theory. So the idea is, let's restrict our attention to counterfactuals within a particular scientific theory. Once we do, the models of the theory will then count as the worlds. This is safe for the staunchest empiricist, right? Because this doesn't commit them to anything more than they would have committed themselves by using or accepting the scientific theory. And it uses similarity of, say, empirical predictions. So it makes the similarity relation entirely precise. One of the nice things that you can show is that, as I mentioned at the beginning, a slightly stronger sort of structure, something called a uniform structure, often arises in these sorts of situations where the way that we encoded the topology is through similarity of empirical predictions. So this encoding is often strong enough to give us a uniform structure, and you can prove that a space with a uniform structure turns out to be models for certain of Lewis's logics of counterfactual conditionals. So in other words, one can use the apparatus of Lewis to do modal logic of counterfactual conditionals and normal modal logic entirely internal to a scientific theory, provided with a similarity relation. So the goal here is not, as Lewis had it, take our accepted counterfactuals and try to reverse engineer what our accepted similarity relation is. But think about what's the relevant similarity relation for a particular explanatory context, and use that to evaluate scientific counterfactuals. Okay, so I'm going to conclude here so that I have a few minutes for questions. I've tried to give you some evidence that putting topological structure on scientific theories has the promise to allow impressive progress on a range of philosophical questions. Its formal tools, in particular, provide the means to precise answers. And they also force us to think harder about relevancy and the choice of similarity relations. In a particular explanatory context, in other words, what's the relevant notion of similarity? I think this work on counterfactuals suggests a new view of scientific laws that I haven't had time to talk about, but we could talk about afterwards if you'd like. And I'm also curious if you have ideas about other subjects or questions that it might shed light on. Thank you for your attention.